In section 1.7, we're going to look at linear inequalities. A linear inequality is an inequality that can be written in the form a times x plus b is less than c, where a, b, and c are real numbers and a is not equal to 0, because if a were to equal 0, we would lose our only variable term. The less than symbol in the inequality above can be replaced with any of the three other inequality symbols as we see here. We can have strictly greater than, less than or equal to, or greater than or equal to as other possible symbols. The procedure for solving a linear inequality is very similar to that of solving a linear equation, with one exception. Anytime we multiply or divide the two sides of an inequality by a negative number, we must reverse the direction of the inequality symbol. Otherwise, the procedure is exactly the same as when solving an equation. We can add or subtract the same quantity to the two sides without making any change to the inequality symbol. We can also multiply or divide the two sides of the inequality by a positive number and not affect the direction of the inequality symbol. In our first example, we have negative 7x minus 3 is strictly greater than negative 8x plus 6. We will try to isolate the variable term and then isolate the variable x. We start by adding 8x to both sides, which would give us x minus 3 is strictly greater than 6. Next, we can add 3 to both sides to get that x is strictly greater than 9. The instructions ask us to express the solution in set builder notation. Set builder notation looks something like this. We'll say that the solution includes all numbers x such that x meets the condition of being strictly greater than 9. That vertical segment stands for the words such that. In our second example, we have that 5 halves times x plus 4 is strictly less than 2/5. Just as with solving equations that include fractions, we may want to clear the denominators as a first step. In this case, we can multiply the two sides of the inequality by 10. Let's go ahead and do that and see what we get. So we have 10 multiplied by 5 halves x plus 10 times 4 is strictly less than 10 times 2/5. Now let's simplify. 10 times 5 is 50. 50 divided by 2 is 25. So our first term is 25x. Then we have 10 times 4 is 40, less than 10 times 2 is 20. 20 divided by 5 would be 4. Now we can subtract 40 from both sides to get that 25x is strictly less than negative 36. Finally, we can divide the two sides of the inequality by 25. Because 25 is positive, we don't have to affect the inequality symbol. It stays exactly as it was. So we have that x is strictly less than negative 36 divided by 25. Again, using set builder notation, we'll express our solution as the set of all values of x such that x is strictly less than negative 36 over 25, which is a fraction expressed in lowest terms. In the next section of our notes, we're going to look at how to graph the solution set of linear inequalities. And we're also going to practice how to write the solution set using interval notation. Our next example is that negative 4x plus 3 is less than or equal to negative 5x minus 2. We can start by adding 5x to both sides of the inequality to get that x plus 3 is less than or equal to negative 2. Next, we subtract 3 from both sides to get that x is less than or equal to negative 5. We can use the number line above to graph the set of all real numbers that meet this condition. Notice that because this is a weak inequality, x can actually take on the value of -5. So at -5, we are going to use a solid circle, and x can also be any value less than that. So we're going to shade to the left. Notice that x can be as small as it wants to be, and so there's going to be no end to the shading in that left-hand direction. Another way to graph the solution set is to use a square bracket over -5 instead of that solid circle. It means exactly the same thing, in fact. It means that -5 is part of the set. I prefer to use a square bracket because we'll see how it connects to writing the solution in interval notation. The solution set will be made up of the interval that has no lower limit, so we'll use -infinity as our lower limit, and it has an upper limit of -5, which is included in the set, and so we'll use a square bracket as our symbol. In the next example, we have -4x minus 5 is strictly greater than -5x minus 11. Again, to start isolating the x term, we're going to add 5x to both sides to get that x minus 5 is strictly greater than -11. Now we add 5 to both sides to get that x is strictly greater than -6. In this case, -6 is a lower limit. In fact, x has to be greater than -6. It has to be to the right of -6. So at -6, we're actually going to use an open circle to indicate that that is a barrier, a boundary, but that it is not part of the solution set. X has to be strictly greater than -6, so x could be anything to the right of -6 on the real number line. So we're going to shade to the right without ever having to stop. Another way of designating -6 as a boundary that is not included in the solution set is to use an open parenthesis. It's equivalent to using the open circle. I prefer to use the open parenthesis because it translates very well into our interval notation for the solution. We can say that the solution includes all real numbers with a lower limit of -6, but with no upper limit, so we'll use positive infinity as our upper limit. In this case, -6 is not included as part of our solution set, so we use an open parenthesis. Negative infinity and positive infinity are never values that can be reached, and so negative infinity and positive infinity are always going to be enclosed with open parentheses. Let's take a look at three-part inequalities. There are two types of three-part inequalities. In this case, we have -2x plus 3 kind of sandwiched between two values. It must be greater than or equal to -7, and it must also be strictly less than -5. That means that it has two conditions that have to be met at the same time. To solve a three-part inequality, you have to modify the variable term in such a way that you can get the variable all by itself. But whatever you do to that part of the inequality, you have to make sure you do to all three parts of the inequality. To isolate x in this case, I'm going to start by subtracting 3 from all three parts, subtracting 3. So -7 minus 3 will be a -10. -2x plus 3 and then minus 3 will just give us a -2x in the middle. And finally, -5 minus 3 will give us a -8 all the way on the right. Notice that the inequality symbols remain completely unchanged. Next, I'm going to divide by -2 to isolate x. I'm going to write this to remind myself that because I am dividing by a negative number, I must reverse the direction of the two inequality symbols. Dividing by -2, I'll get -10 divided by -2 gives us a +5 on the left. We'll have 1x in the center, and then -8 divided by -2 will give us a +4. Now, this does not seem like a very comfortable way to talk about the restrictions of x, so we can write this in a way that's a little bit easier to read. Basically, we have that x has to be greater than 4. So I'm going to put the 4 first and say that x has to be greater than that. Next, I have that x is less than or equal to 5. So I will write that as my upper limit. Note that these two three-part inequalities are completely equivalent. They mean exactly the same thing. The second, however, is a little bit easier to read and interpret. In terms of our solution set now, I can say that the solution set includes all real values of x with 4 as a lower limit and 5 as an upper limit. 4 is not included in the solution set, so I'm going to use an open parenthesis to enclose the 4. 5, however, is included in the solution set, and so I will use a square bracket. In the next example, it looks very similar. We're going to subtract 3 from all three parts to start isolating x. So if I subtract 3 from 9, I get 6. Then we have that less than or equal to 2x, and that'll be less than or equal to 10. This time, I'm going to divide by a +2. Dividing by a +2 will not affect the inequality symbols at all. 3 on the left, x in the center, and then we'll have 5 on the right. In terms of the solution set, we have 3 as the lower limit, 5 as the upper limit, and in this case, both 3 and 5 are included in the solution set, so we will use square brackets on both sides of that interval. I failed to graph the solution set for number 1, so let's catch up and graph both of these solution sets. For number 1, the lower limit was 4, but 4 was not included, so I'll use an open parenthesis there. 5 was the upper limit, and 5 was included, and so I'll use a square bracket there. Boy, this is small and hard to read, but it'll look something like this. Let me replicate this a little bit larger. So here's 4, here's 5, open parenthesis, close bracket, and then shading in between. For number 2, the solution set goes from 3 to 5. Again, this is very, very small, but I will use square brackets on both of those and then shade in between. Notice that for three-part inequalities, the solution sets will always be intervals. Finally, we'll look at compound inequalities. Compound inequalities either include the word and or they include the word or, and they do mean different things. In the first example here, we have that x minus 3 must be less than or equal to 1, and at the same time, x minus 3 must be greater than -4. We can solve each part of the inequality individually. First, by adding 3 to both sides of the first inequality, we get that x must be less than or equal to 4. And at the same time, by adding 3 to both sides to the second inequality, we get that x must be strictly greater than -1. Let's take a look at the graph of both of these inequalities separately. For x to be less than or equal to 4, we would have 4 as an upper limit that is included, and we would shade everything to the left without a lower limit. For x to be strictly greater than -1, we would shade at -1. Oh, I guess I did not do that part properly. Let's try that again. These are so small. In fact, let me just do a new number line here. X must be strictly greater than -1, and it must be less than or equal to 4. I think this will be easier to see. So 4 would be an upper bound, and we could shade to the left of that. But because the second condition has to be met, X must be strictly greater than -1, so we'll have an open parenthesis for that lower limit. That means that our solution set is the interval that has -1 as our lower limit, not included, +4 as our upper limit, which is included. The last example for this section is one that has a compound inequality with the word or. So I really want to highlight the difference between how we're going to treat and problems and or problems. We're going to solve the two inequalities separately. 7x minus 9 is strictly greater than 5. We can add 9 to both sides to get that 7x is strictly greater than 14. Dividing both sides by +7, we get that x is strictly greater than 2. For the second inequality, we have -x plus 7 is greater than or equal to -8. By subtracting 7 from both sides, we'll get that -7 is greater than or equal to -15. Now, to solve for x, we will divide both sides by a -1, or multiply both sides by a -1, which is equivalent. We'll get positive x on the left, we'll get positive 15 on the right, but because we divided by a negative number, the direction of the inequality will be reversed. Now, this one's going to be a little tricky. Or means that x doesn't have to meet both criteria at the same time. It could be either one. So if this had been an and problem, 2 would have been our lower limit and 15 would have been our upper limit. But let's see what happens in this case. X could be strictly greater than 2. So let's shade what that looks like. Basically, that's everything to the right of 2 without ever stopping, no upper bound. Or x could be less than or equal to 15. Well, let's say 15 is somewhere up here. And so we'll have 15 included, and we'll shade everything to the left of 15. But we can go past the 2. In fact, we can go past any number we want off to -infinity. Because this is an or inequality, this means that x doesn't have to meet both criteria. It could meet one or the other and still be part of the solution set. Because we've essentially shaded the entire number line, the solution set is going to be the set of all real numbers, which we'll write as the interval that goes from -infinity to +infinity.